All right. I think it's time to start. How many of you have started homework? 0? Great. It's too hard. Don't worry. We're gonna lower the weight of homework 0. I mean, as long as you can try your best to finish, and rather than decide to drop the class, we're gonna lower the weight of homework 0, so it won't take too much ratio in the final grade. This is just to, I mean, first test your background, second test your flavor. I mean, if you feel pissed off by those questions, or if you feel like struggling in these questions, then you might need to consider for that. But you feel it's okay, but it's a little bit harder. But I might take more time, but I'm comfortable to deal with them. That's totally fine. And also you guys can form some like study session or discuss about how to solve that problem. The only request from us is that we want you to write down the solution by yourself. Don't just copy their text, LaTeX source. That's not allowed. But as long as you can, you can figure out how to deal with each problem, you can solve them and write down this by yourself. That's fine. I don't think we're gonna extend. I mean, just try your best to do that, and use that to gauge if this is something you feel interested in. I'm pretty much sure. I mean, in the later homeworks, that won't be that hard because this is kind of like testing your calculus and linear algebra things. This shouldn't be my job. This shouldn't be my job. This should be your instructor in calculus 1, calculus 2, whatever, right? Or in linear algebra. But this is just to force you to open the books and try to review those concepts. You feel unfamiliar with that, and but if you still feel extremely struggling, I mean, if you're struggling at a few questions, that's fine. But if you're struggling with like half of those problems, that can be problematic. And also, please leverage the office hours. Like yesterday, when I sit here, I only have one fellow came to me and asked my questions, and no one else stopped by. Yeah. Please feel free to ask questions. We got office hour every weekday. All you guys can also post questions on Canvas, but we cannot guarantee like immediate response, right? Okay, yeah. I mean, regarding regarding the postpone, let me think about it. Let me think. I have to make decision tomorrow night. I mean, right before the deadline. I'd like to see how many submissions are made. What? I thought you were reviewing just to check out some theorem or some results, how to read the books from page 1 to page 200. Okay, so yeah, but if you want to complain something, just feel free to text me. So first, I mean, send me a message or come to the office hour. That's fine. But you guys really don't need to worry too much about the grade of homework 0. We're gonna downweight it. Of course, we're not gonna downweight it to be 0, but it won't be viewed as important as the following homeworks, because those homeworks are really about the course content. This is just some warm up, some review things. Okay, so let us continue. So in the last lecture, when we review some basic concepts, we talk about matrix vector derivatives and the definition of convex functions, and etc. Right? We actually introduced a very important dual is called convex conjugate or French-Held duality. Right. So I have pointed out some references in the lecture video page. So if you want to know more about that, you can take a look at that. And someone asked if I can show some detailed example to calculate that. Well, the homework, there's one homework problem asks you to do that. And if you want to see more examples, that reference, that is just 3 or 4 years, 3 or 4 pages in the PRML book. You get a sense how it is embedded in the variational inference framework, which we're gonna cover. But right for now, you don't need to know what is variational inference. You just need to know this definition and try to capture the geometric meaning of that, because it will be help you better understand the duality. But if you want to calculate, you just follow the definition. Just follow the definition. If you want to get g of lambda, you construct this function, right? At any particular lambda, right? So you can view this function of x only, right? You just maximize this function. How to maximize it? Take the gradient, set gradient to be 0. Right? You find the corresponding lambda, you got the value, right? So this is it's really straightforward to, derive something based upon that. But here, I just want to quickly go through the geometric meaning to give you a sense. It's I don't request you to follow that like in 1 minute, but just to keep that impression. Later you can take a look and you'll see that it's not that intuitive, but once you have some kind of impression in your mind, it will be a lot helpful. Okay, so we can start with this g of lambda, right? This that duality. Can you share sort of the list of what previous projects people have done in the past? So I think this notes was available for years ago. So what kind of projects people have? There are like very overview concepts on the website, but you can share sort of a list of projects people have. Yeah, I can definitely share with you guys, but you can also take a look at the course webpage. Yeah, there's a project webpage. You can take whatever the example projects there, or you can you can read papers. You can take what I think. I recall in my recollection, quite a few students or PhD students, they just brought their research projects. Say, hey, professor, I want to do this. My advisor suggests me to try probabilistic learning, so I want to do this. And I said, cool, right? Why not? So feel free to bring up your ideas. But later I will share several such kind of projects in the Canvas for your reference.
I have a question about projects. It seems that G might be a non-linear function. I mean, takes infinity.
Yeah. This is not very rigorous. Definition. If you talk about more rigorous definition, this should be superior. It's not max. But let's just put aside this. Don't think about those corner issues, because of course you can. This theory applies to complex functions as well, but we're not gonna talk about that.
Yeah. I don't get the context. I mean that it is possible that the maximum is not taken by to be real value. Just
that is the problem you just mentioned.
Yeah.
That's why I said why we should. Rigorous notation should be supreme, not maximum. Because in some open set, if your convex set is open set, actually you cannot find maximum. You can only find supreme. Yeah, that's a very good point. But it's a little bit. Practically we won't care about that. Yeah. Okay. Yeah. So let us look at the geometry meaning for this, right? So this I can tell you this concept is just this just tells you this g of lambda just tells you for a convex function f of x here, right? So you can use lambda to construct a function lambda x, right? It's a line. Lambda is actually a slope. G of lambda actually tells you if you want to use slope lambda to make a tangent line for f of x, then G of lambda, sorry for the bad drawing. So G of lambda is negative of this intercept of the tangent line. That's the idea. I mean, to see that point, I want to quickly repeat the example we have shown before. Okay. Oh. Okay. So suppose you choose lambda here, right? This is your lambda x. So this is your slope, right? Lambda x, lambda indicates slope, right? So from the definition, you want to say which value at which particular x that makes the difference between lambda x and alpha x maximum, right? So if you look at the difference between lambda x and alpha f of x, right? So at different x, right, you can just look at this vertical segments, right? There actually indicates that different x. What's the difference between lambda x? This is a straight line and this curve f of x, right? So in this part, remember, fx is here. Fx is above lambda x. So their difference is negative. Of course, it's not maximum because this is negative value. Of course, I mean, similarly, for this part, because f of x is also above lambda x, so their difference, lambda x minus fx, is still negative, right? So we should find the maximum length, maximum difference in the middle. In this part, right? In this region, right? You know, the optimal x should stay in this region because in this region, lambda x stays above f of x. So their difference is bigger than 0. Okay. You have a question? Okay. So of course we know the maximum difference must be somewhere here, right? Or here, right? Visually, right? But the problem is how do we find that, right? How do we find it? We can just move lambda x downward, right? We move it until you kind of tangent. You kind of become tangent line of f of x, right? And the intersection point of this tangent line and f of x is the place where this difference is maximum. Does it make sense? Right? The reason is that, okay, you can draw any line between, right? No, it's not. You can see that all the other difference is here, right? So only this part is the longest because if you want to get the same length, you have to extend. You have to extend those small segments downward until you reach this tangent line, right? That means only this segment in the middle is the longest. Does it make sense?
What's the problem with maximum?
You want to know why this is useful, right? You want to know why they formulate this weird. Why do you give us this weird formulation? Oh, we'll come to it later. Yeah, here is just give you this formulation exists there, and later we'll see it is very useful because I mean, in probabilistic inference, those f of x are often representing some kind of probability prior or likelihoods which are highly complicated. So if you do some variation inference, you want to estimate posterior distribution, it's very hard to compute. However, if you use this formulation, you can see that the right-hand side now becomes a linear function to x, right? Given any lambda, this guy actually is linear function to x. So what you need to do, okay, given any x, I can maximize the lambda to approach f of x as much as possible. So doing the inference procedure, okay, I can replace f of x by this linear function. Then I can make my computation a lot easier. The cost is that, okay, I need to optimize an additional parameter lambda. That's the idea. So we'll talk about the example later.
What if we say conjugate of the conjugate function?
There is some kind of trick doing that. I mean, if you
back to the original?
Yeah, you get back to the original. I mean, if you take the conjugate and do it back, you get back to f of x again. But the problem here, you can do some kind of nested conjugate. I mean, if you do some conjugate, if you use some convex conjugate to replace the original function, and then you kind of merge some. If that form is still kind of complicated, you can merge those complicated terms again. And if you can show that, okay, they are convex, I can apply that again. This is kind of a trick used to construct variational model evidence lower bound. So, yes, G of lambda is a convex conjugate of f of x. Okay, I'll tell you, we'll introduce this when we talk about variation inference. But if you want to take a look, you can try to calculate, say, f of x is negative logarithm of x. Try to compute its convex conjugate. You got a sense. But from geometric meaning, its convex conjugate is just the negative intercept of the tangent line. So why this is useful, right? So let us go back to the representation of f of x. So we know that g of lambda is actually the negative intercept of the tangent line, right? With slope lambda. That means this guy, lambda x minus g of lambda, is actually the tangent line, right? Lambda x plus intercept is the tangent line. Now, g lambda is negative intercept. I subtract by g lambda. It is just intercept, right? Okay. So now you can see that the right hand side, the first equation is actually a tangent line of your convex function with slope lambda, right? So now we can see. Let's check the rationality of
of this form of this first first equation, right? So again, I'm gonna draw this convex function f of x, right? So if you take a look at the right hand side, it's just given any particular x, right? When you vary lambda, you're actually varying the tangent line, right? So we can, for example, you got one lambda, which particular lambda here, right? You got a tangent line here. This is lambda 1, x minus g lambda 1, okay? You can just vary, you just random pick up another slope, lambda 2, right? This is lambda 2, x g lambda 2, okay? So the right hand side actually is asking, how do I tune my slope such that at this particular x, the value of my tangent line is maximum, right? Because we're taking maximum, right? So now who can tell me what particular lambda can give me the largest value at the tangent line at x? You can see that this guy obviously is not the best, right? And this guy is even worse. You can imagine you can always vary the slope, right? And try to get a tangent line. Which one can give you the largest?
All the time, the line is located here. Because
Yes, this is the convex functions property. Yeah.
So that one is always is negative, and so the maximum is just if it is tangential to that point.
Yes.
Like that.
Yes, exactly, right? Yeah, this is actually comes from the convex functions property we mentioned before, right? So for any function body, I mean, for the whole function body, any tangent line will stay below the entire function body, right? So that means no matter how you vary your lambda, the value of the tangent line at any x will be less than or equal to f of x, right? But if you want to make that value maximum, you're gonna make your tangent line right pass through this x, right? And then the value at that point actually is the same as the f of x. So this is what the first duality tells you. Any question?
For example, in the example of vector of x, you can find that constant time.
I need to calculate.
Yeah.
Yeah.
So positive number,
Yeah, I mean, lambda is not, not necessary to be total free. It also dependent on the original function. Right? But this is just tells you, I mean, you can double check. I mean, if you want to calculate g of lambda, you just maximize lambda x subtracted by log x. That'll be something like that, right? And then you just, this is x. Right? And then you just, take the gradient and then find the optimal lambda. Yeah.
that's clear. The number is positive, and since x is positive as well, the maximum would be n.
Positive as well is I didn't get a point. So
You know,
so you want to calculate maximum x lambda x subtracted by, no, it's
plus
log x, right? Yeah. So here, first you need to observe that x is positive, right? Of course. And then when you solve this problem, it's become, well, then your x is minus lambda. Yeah, you're right. Yeah, lambda must be negative. Yeah. Okay, I will leave this as an exercise for you guys. I mean, but as you mentioned, you cannot assume lambda is free over R all the time. It really depends on the definition of f of x. Okay, so now we're gonna talk about fundamental concepts, right? So we can view our course schedule is like level by level, right? At the bottom is very basic concepts. I bet everyone has heard most of them, and then up down one level, we're going to talk about each distributions, right? Commonly used distributions, some of what is the concept of conjugate distributions, what is this exponential family, what's the nice properties of the exponential family, and then based upon that, then we'll talk about a variety of different probabilistic models and how we do the model estimation, how do we calculate the posterior distribution, and so on. So we're going to start with the basic concepts. Again, I believe everyone has heard most of those concepts, but here I just want to give you a more systematic view. So first, we're going to introduce what is sample space, right? And remember, when we'll talk about any probabilistic problem, always associate a probability structure in your mind. That is a probability space. So probability space is a triplet. First, we're gonna define what is a sample space. Second, you're gonna define even space. And if you have heard some, if you have taken some measure theory before, this is usually called sigma algebra. And then you're gonna assign a probability measure. So probability measure is a mapping between the set and some number between 0 and 1. So later we're gonna give you some concepts, but anyway, those are just some fundamental concepts. We're not gonna talk about what is the measurable, what is the if you want to make your if you're given some sigma algebra, how do you construct other sigma algebras? We're not gonna talk about that, but you should have some basic idea that the probability models or theory is based upon measure theory. It's not based upon, I know how US taught undergrad students about probability, but in China, they just ignore everything about measure. That made me a lot of confusing for a long time when I really did research. So I have to take a look at what is the more rigorous definition about probability. But here, I just give you some key concepts to have that in your mind. So later, in the future, if you want to go deep in that, you can take some probability measure theory class. Then you will know a lot of like fundamental derivations. What is independence? Right? What is conditional independence? Those all have a rigorous definition based upon measure theory. Okay, so when we talk about probability space, right? We need to first talk about sample space. So what is sample space? So you can view like, okay, you're doing some random experiments, like maybe you're gambling, right? Or you just come out to check out to the PM 2.5 concentration, whatever. So anything you will it as some kind of randomness, you can view as you're doing some random experiments. And the sample space is just a set which consists of all possible outcomes of the random experiments. Okay? So for example, if you're just toss a corn, right? Toss a corn, and then your sample space might only have two elements, heads or tail. Right? If you are rolling a die, right? In Las Vegas, right? And then your sample space might just 1, 2, 3, 4, 5 to 6. You have only 6 points in your dice, right? And or maybe you just test the radioactive decay after some nuclear experiments, right? And then you got your device, right? Read out the number of particles emitted per minute. Then your sample space is all the natural numbers, right? 0, 1, 2, 3, 4, 5. So, and also we have like continuous examples, like if you want to measure the height of spruce trees, or you want to look at the image pixel values, right? So those are continuous space. Well, will sample space are set of subset of R, the real space, or yeah, and the interval in a real line, and etc. But anyway, in general, sample space just tells you if you do some random experiment of your interest, what are the possible outcomes. And then given the sample space, we can define event, random event. Like suppose I'm doing gambling, right? I roll a dice, I roll a die, right? So I can create an event. Okay, my point is bigger than 5 or not. This is one event. Okay. And this event can represent by a subset of the sample space, right? Like if my event defined as okay, my point is bigger than or less than 3. So what's the corresponding set? Just 3, 4, 5, 6. Okay. And in the spruce tree example, right, consider you have an event that the tree is taller than 80 feet. Remember, our sample space will be all positive numbers. So this event can be represented by a subset of your sample space, which is just interval 80 to infinity. Okay. So in the abstractive level, right, we can define event in the sample space omega is some subset of the sample space. So when we study that random system, right, we need to define the whole range of events we're interested in. Right? What set of events we think are meaningful, useful, or interesting. Right? So that's all sets of events. The collection of all events we're interested in is called event space. Let me. It's called event space. So someone asked, why not I just use power set of your sample space, meaning that I just enumerate all possible subsets of my sample space to construct my event space. Yes, of course you can. But you should keep some kind of flexibility, right? You can allow some guy to define, to focus their interest in some smaller range.
Subsets.
What?
I think we need to be measurable.
Yes, yes. We're going to talk about a point in a minute. So, so that's called event space, right? So, but when we talk about, you got a set of events, right? You got event A, you got event B, like A1, A2. Suppose all those events are inside your event space. We know that from set operations, we can create new events. Right? As we mentioned here, if we got two events A and B of a sample space, you do a union of A and B, you create a new event. That event should be valid, right? So this event just tell you, okay, A happens or B happens. Okay. And you can use another set operation like intersection. This just tells you, okay, both A and B happen. Or we can use a complementary operation, right? Like even A, that then this complement of A just means, okay, A does not happen. This is another event. Or subtraction, like even A happen, but even B does not happen. Right? So I mean, naturally, we request that through this set operations based on existing events, we can create new valid events. Right? This is very natural. So now the problem is, suppose I have a defined even space, right? This should be the whole set of events we're interested in. Then you should guarantee that doing this various set operations on the events inside your event space, this new event should still belong to the event space, right? It shouldn't get out. Right? This is called closeness, right? You should allow those events to do some arbitrary union, intersection, completion, subtraction, and it won't generate some event out of your scope. So these things actually put some restriction on the definition of even space. Not all subsets, not all collections of subsets in the sample space can be called even space. Meaning that you cannot like randomly draw like 100 subsets from even space to form your from sample space to form your whole even set. Your even space must satisfy a few criteria to ensure the closeness. So what kind of criterion should your even space satisfy? So we usually choose these three criteria. So first, we request that the empty event must belong to a even space. Second, your even space is closed under finite under countable union of events. So countable, I mean, it can be finite countable or infinite countable. Meaning that, okay, you can index your event by natural numbers or integers, right? It can be infinite number of events, but their corresponding sets, when they do the union together, you must ensure their union belong to your even space as well. And the third property is that it is closure under completion. If even A is in your even space, then its completion must be in the even space as well. So if you can pick up a collection of events which can satisfy the three properties, then your even space is valid. And such even space is called a sigma algebra. It's a very weird name. I don't know why they give this name, but this is called sigma algebra. Any questions so far? Is everyone good with this? Mm-hmm. Oh, it's power set. It's just enumerate all possible subsets in omega. So power set of your omega, I mean, of your sample space is ensured to be a sigma algebra. But of course, I mean, in many cases, you might just want to take
not many subsets together to form your even space, right? And in that case, you need to satisfy these three conditions. Otherwise, you will have some like paradox. Like if you're interested, you can look at is a Banach-Tarski paradox. It's a very motivated example to tell you why they're gonna define those things. Okay, so once we have defined sample space, right? And we also define all the range of the events we're interested in. Now we want to measure them, right? We want to characterize how likely each event is gonna happen, right? So the third component in our probability space will be a probability measure. So why it's called measure? Because measure is not the function we often saying. Like when we talk about the function, we're always assuming, okay, it is a mapping from r to the power of d to some r, right? But the measure is a function from set to numbers. Right? So so probability measure is actually take any event in your event space. Remember, event is a set, right? And map this set to a number between 0 and 1. This is why it's called probability measure. So we can view, okay, this is your different events, right? So there are different sets, right? So you're gonna assign the chance that each event happened, right? So you're gonna map each of the subset to some number like 0.5, 0.1, 0.6, 0.2, right? So this is what the probability measure does its job. But in a more general sense, if you don't want to give my measure a probability sense, I just want to measure the volume area, right? It's not necessary to be between 0 and 1. It can be 3 or 4, right? Like what's the area of this ellipsis or circle, right? It could be 3 or 4, whatever. So in that case, you're gonna define measure function. And probability measure is just a special type of measure function, which requires your measure must be between 0 and 1 because they have some probability meaning. So, and of course, for a probability measure, we have some requirement. Your probability measure must be intuitive, right? For example, for empty event, you should assign 0, right? You shouldn't assign an empty event or empty set with 0.9, right? That doesn't make sense. So first, we require your probability measure on empty event to be 0. And second, we require that for pairwise disjoint sets A1, A2, I mean AN, whatever, that belongs to our even space, the measure over the union of those sets is the summation of the measure over each individual set. This is reasonable as well, right? You're like you have an even A, you have an even B, you have an even C, you have an even D, right? And the union of those, sorry, let me put D here. The union of these events is just telling us, okay, I'm gonna have another event, which tells us that event happen means A or B or C or D happen. Okay? So of course, their chance is larger than the chance that each individual event happens. So we require that if A, B, C, and D are kind of independent, then the probability that the union of those events happen is the summation of the probability each event happens. And thirdly, as you mentioned, it is a probability, right? So your whole set its probability measure must be 1, right? I mean, it's all possible. I mean, this whole set omega just means I think it's hard. Like for example, one event is I'm alive, the other event is I'm dead, and the whole set just tell me I'm alive or I'm dead. So you tell me this is always true, right? This is always the truth. So probability is 1. Okay, any question? Just some conceptual definition. We won't talk about I mean the details about some axioms behind that and what is the rules to conduct the probability measures over the more complex set operations. I just give you some conceptual introduction of the probability space. Is that everyone good? Okay. So a probability space is a triple, which consists of 3 elements. First, omega is the set or whole set is called sample space, including all possible outcomes of your random experiment of interest. F is a sigma algebra. It's called event space. It actually includes all possible random events you are interested in. And third one is a probability measure, right? It actually characterizes or models the chance that each event happens. Right? And of course, to make your probability space reasonable, you have to satisfy the conditions we just listed. So here are some common properties of probability measures. I think everyone has seen this before, but usually people will take out this measure, but they're actually the same thing. So like for any probability measure P and even A and B, then the probability of completion of A is 1 minus P of A, right? And in general, the probability of A union B is probability of A plus probability of B subtracted by probability A intersection B, right? So this can be explained using this Venn diagram, right? So I mean, in general, we don't assume A and B are disjoint, right? So they might overlap. So when you add P of A plus P of B, then the measure over the intersection part is counted twice, right? That's why you're gonna subtract it. You're gonna be subtracted by this measure over the overlapping part again, right? And the conditional probability. Conditional probability is defined as follows. Suppose I'm gonna have I have an even A and an even B, then I can define the probability of A given B by dividing the joint probability of A and B by P of B, the marginal probability. So here just want to emphasize this a little bit. So we write P A comma B, right? This is a very common use notation, right? This is actually indicates you're calculating the probability of A union B. It's not the probability, oh, not union. It's probability of A intersecting with B. It's not the probability of A union with B. So don't be confused. Because we know that, I mean, from our notation, we know that P, A and B less than or equal to P of A and P of B, right? But if you do this union, it will be bigger than P of A and P of B. Okay. So just be aware. So here's just one example. We're rolling a die, right? And the measurement of each individual example is 1/6, I mean, uniform chance, right? So suppose what I got even A represented as set 2, right? And even B represented by 2, 4, 6. And we know P of A, the marginal probability is 1/6. And then I can calculate the conditional probability of A given B by dividing the joint probability by
the marginal probability B, right? So PA intersection with B is just a 2, right? Which is just 1/6. And then the marginal probability, because marginal probability of B consists of 3 elements, right? So P of B is half. So you can divide it, and then you got this conditional probability to be 1/3. Any question? I mean, I'm gonna going through this real quick because I believe everyone is familiar with this, right? So then we can define independence, right? Let A and B be 2 events in a sample space. We say A and B are independent if P, A intersection with B, is the product of their marginal probabilities, P of A times P of B. And 2 events are not independent, it's called dependent. So if this equality does not hold, then we say A and B are dependent. And dependence can be defined in another way. That is, if the conditional probability of A given B is the same as the marginal probability of A, then we could say A and B are independent. So we can show that this definition is equivalent to this definition. Okay, so it's pretty straightforward. I'm not going to show that. So here are some often used equivalent conditions to justify if A and B are independent, right? The conditional probability of A given B is P of A. The conditional probability of B given A is P of B, or the joint probability equals to P of A times P of B. The 3 conditions are totally equivalent. They can all be used to prove that your A and B, your 2 events A and B, are independent to each other. So random variables. Random variables. So first of all, random variables are not numbers, values. Random variables are not random, or not variables. Random variable is a mapping, is a function. This is very different from maybe you haven't heard before, at least in my undergrad study. I thought random variables are just some numbers which have some randomness, but actually this is wrong. So what is random variable? Random variable essentially is a mapping or function which map from the sample space to some other set. This space usually chosen as a real space. This is called random variable. So you can view as mapping. So the number, no matter it's real numbers, integers, or complex numbers, they don't have randomness. Randomness only comes from your random experiments, right? Your dye results, or your corn, your head of your corn, right? Those have randomness. So, but because they come from all different experiments, right? And they have different nature, so it's hard to unify them and study them. So that's why people kind of develop this concept called random variable. They want to map those real random things to some number in the real space. And in this real space, or in whatever abstract mathematical space, and then you don't need to care about the original things, right? You just care about this abstract space, and then you can study their properties, and you can extract some commonalities and do some analysis. That's why they define a so-called random variable. Right? So when we write a random variable x, right? So it implies that it has some input omega. This omega is some element your sample space. So maybe it is your corn's head,
it is your when you roll a dice, what is the point? Or maybe it's just a temperature in your read, right? Though it can be anything in your sample space. And then the random variable is in charge of map this guy to some abstract space V. Like this space can be like just integers or real value. Of course, you cannot construct any mapping from the sample space to real space as a random variable. To be a random variable, you must satisfy some properties. It's called a measurable. What is measurable? I'm not going to talk about what is measurable, but you can view like you must be measurable. You must make it to be measurable because otherwise you cannot calculate what is the associated probability. Right? You map some guy to another space, right? Now I want to say, okay, in this space, when I collect a bunch of points, and then when I remapping back, I have a set of samples in a sample space. I must be able to assign probability on this set. Right? Otherwise, your probability system just failed. Right? So if you can guarantee that, okay, any reasonable set in your mapped space, when do this reverse mapping, your original probability system can still assign a valid probability measurement, then it's called measurable. Okay, but just give you a sense. This is a variable, but anyway, in our class, you can by default assume, okay, those random variables are just measurable, valid things. You don't need to worry about they're bad. Here, just some example. Suppose your sample space are just the space of the dice, right? And you're rolling a pair of dice. You have rolling a entire dice. Of course, your sample space will be like 1, 1, 1, 2, right? Just the pairs of points, right? 1, 2, 6, and 6, right? You can define your random variable to map any of these dice point pair to another space, say another integer, right? So here gives a very simple definition of random variable. It's just the summation of the numbers on the two dice. Okay, so your random variable, which maps the dice sample 1, 2, it will give you the value of 3, right? 4, 4, give you the value of 8, 6, 5, give you the value of 11. And even simpler example, like if your random experiments the outcome of a random experiments are real numbers, right? And then you can simply take your random variable to be an identity mapping. That means I don't make any special processing of those original samples. I just map them to itself. Then your random variable is the sample themselves. The benefit of using random variable is that you can define events on top of random variables, meaning that you can define a collection of the possible random variable values. Then you know that this collection of the random variable values will correspond to some event in the original probability space, right? So, for example, you can define, this is your random variable, right? If your output random variable is X, right? We define this event essentially is the set of the samples in the sample space such that X of S equals to this particular value. Does it make sense? Remember, random variable is mapping, right? Mapping means that, okay, many
the same, the different inputs can be mapped to the same value. This is your random variable. So this is your sample space, right? So these 3 samples might be mapped to the same value, Cx. So when we define this event, big X equals to small x, it's just indicating the event that event set which include all these 3 original samples. And perhaps the more commonly used is something like that, right? Big X, the random variables outcome less than X. It actually corresponds to the event, which is a set in the original probability space such that they satisfy X of X less than X. And accordingly, you can define an inequality, right? A range A less than X and less than B is just the set, the even set, not an even set, it's just the set where A less than X of X less than B. Okay. So when it is very convenient for us to write the probability that something like that, right? So when we do a lot of things, right? When we use probability, when we reason with probability, right? It is very common for us to like a probability of a random variable X less than 3, right? So what's that meaning? It actually means I'm gonna assign the probability measure over the set that the mapping of the samples is less than 3. So of course, when we talk about this, we always use this by default, but please beware the underlying meaning. It's still kind of a remap back to the original sample space and take the probability measure on the corresponding set. And now that it is so convenient to define events in terms of the range of probability, range of the random variable values, right? So people kind of pick up a particular type of events. That is, given some particular x, right? I want to know what is the probability of your random variable value less than or equal to x. Remember, you are always map back. This corresponds to some set your even space. You should be able to assign probability on that. Okay? So, but on the other hand, you can view this guy dependent on the choice of small x, right? So it's essentially a function. Right? Any x on the right-hand side corresponds to the probability measure over a set of samples. Or in other words, a particular event in the original space, okay? Which will be between 0 and 1. Okay? So this actually defines a function. So this function is called a cumulative distribution function, CDF. So I bet everyone has heard of them, and used them before, right? But usually we just will, okay, there is some probability here. I can view this. This probability just varies with x. So we can define this as a function. So this so we call this a CDF function, right? But just to give you a sense, what's the underlying meaning? Any questions so far? Is everyone comfortable? You mean the meaning of this? Okay. So this inequality actually associates with a particular event, right? This event is defined. Remember, even is a set, right? And the random variable is a function, is a mapping, right? So the corresponding event in our probability space is the set of samples, right? Set of samples whose random variable values satisfy this inequality. So this is a particular event that belongs to our event space. So when I talk about the probability of big X less than or equal to small x, right, we actually talk about the probability measurement over this set. And of course, this probability measurement will always between 0 and 1. Right? And of course, when you vary X, your corresponding set or event will change as well. And then your probability measurement over that event changes as well. So this changes as well. So that's why this guy defines a function. Right? Different X correspond to different event in the original probability space, and then corresponds to different probability measurement. Right? It varies along with small x. So we can define a function in terms of x, which we call the cumulative density, cumulative distribution function. And I think the most in most cases we just ignore this step. Most people will ignore this step. Okay, we'll see mostly this guy. This one tells us okay, there's a number of 1, and it varies along with x. That's fine. I mean, you can use it by default, but you should be aware there's some kind of underlying mechanism to give you that. So the if you take your random variable to be real valued random variable, meaning that you map your sample space to some real space, right? And then this cumulative density functions has some nice properties like monotonic increasing, right continuous, and when x goes to negative infinity, this is 0. When x go to positive infinity, this is 1. I think everyone has learned this before, right? And but I can tell you this two and this property need rigorous proof under the measure theory context. But here, let's just use them. Let's just use them. This is about the real valued random variable, right? If you define your random variable, the output is discrete. Then we usually do not talk about like cumulative distribution function. We call it probability mass function. So then we're interested in the probability that the random variable value equals to some particular discrete value. Right? That's something we often use before, like when we already calculate the probability that your bulb is your light is on or off, right? And you assume okay, your random variable outcome is 0, 0, or 1, right? This is essentially to map something in some probability space to 0 or 1. Your range of your random variables output is discrete. And of course, you can define your cumulative density function, a cumulative distribution function in terms of mass function, which is it's the same thing, just adds up all the things together. If your cumulative distribution function is differentiable, then we can take the derivative of your cumulative distribution function, right? So this derivative called a probability density function. In other words, we can write our CDF as an integral from a negative infinity to x, right? For your with your probability density function. So this is the integral, and in most time, we're gonna look at this probability density function, and they have a lot of properties, and also there's a lot of like computational issues along with that. So here, just give some example, right? So if your random variable x follows a uniform distribution, so everyone knows that, right? So that means the values of x, the outputs of x is uniformly distributed between 0 and 1. Then we got your density function to be something like that, right? It's between 0 and 1. This density is 1. And in other places, the value is simply 0, right? And if you write the cumulative distribution function, it will be something like that, right? So before 0, it's just 0. And then it's just a line with slope 1, right? And after that, the value will be simply 1, right? Any questions so far? Yeah, really, these things are, everyone has seen this before, right? And transformation of random variables. Suppose I got a random variable x, right? After some kind of transformation y, I got another random variable y, right? So suppose associated with x, there is a probability density p of x, right? And after transformation, of course, it has a probability density p of y, right? And the interesting thing is that the interesting question is that how do I compute the density after the random variables transformation? So here's just the formula. But I want to give you a little bit intuition about that. I'm not give the proof, but I just give you a little bit intuition. And this not only applies to scalar random variables. When we talk about random vector transformations, they actually follow the same rule. So basically, if you have a random variable x transformed to y, right? So basically, in an infinitesimal area, which we usually represent as a derivative, you need to guarantee that the probability measure over this infinitesimal area is the same after transformation, right? This is the basic rule. Okay. If you have a random variable, of course you have some random measure, right? And you can calculate the measure over some small space. Dx is just some small, very, very small. You can imagine infinitesimal cubic, right? And you need to ensure that no matter what kind of transformation you have done, right? After that, after the transformation, of course, you might switch to another coordinate system, right? You got a different dy, right? But the probability measure over this two infinitesimal unit, they should be the same. Right? This is called transformation invariance. Right? And then if you want to get p of y, right, you just multiply p of x, and then this you cannot directly divide dx by dy. So this part is now becomes p of y equals to p of x. Then you need to take the determinant of dx or dy and then take the absolute value. This is the general rule to perform the random variable transformation, how to compute the corresponding density. And remember, you need to take the determinant of the Jacobian, and then take absolute value, because determinant can be negative. Right? And also, this is restrictive in that dx and dy must be bijection. I mean, this guy must be square matrix, right? If it's not square matrix, how do you compute determinant? Right? And this formula is just a special case of this general notation. And although this is kind of like fundamental, maybe you haven't heard them before, but I can tell you, based upon this, I mean, recently in probabilistic learning, there's a very hot algorithms called gradient flow, or auto gradient flow, or inverse auto gradient flow. There's based upon this. If you want to estimate the posterior distribution for some complicated, I mean, for random variable inside some complicated distribution, they want to through a series of random variable transformation to construct more expressive and abundant approximation family. And then in that family, you kind of find the best approximate distribution to the true posterior. So they are based upon this rule. Okay, given the density definition, right? Probability density definition, probability mass function definitions, CDF, all kinds of things, we can define the expectation, right? Expectation is simply the integral of the random variable output and the density function. You can view as a weighted summation of each samples. Mm-hmm.
Can we say something about the joint probability?
From this, it's hard to say. It's hard to say. Yeah. I just tell you, okay, if I know density of x, right, after some good transformation, I got y. I want to know what is the density of y. You can calculate that.
But we can't say anything about the joint.
No, it's not. You cannot say that. And also, x and y, they must be bijections. It's not if x is 3-dimensional and y is 1-dimensional, you can't use that to calculate. And also, a discrete expectation of discrete random variable is just a weighted summation of each possible value weighted by the probability that the random variable takes that value. Right? So usually, I mean, in a broader sense, you can view like integral and summation is actually equivalent. Right? And the expectation has many nice properties, right? So like expectation of ax plus by is a times ex plus b times ey. So it's kind of linear. You can shuffle your expectation into each particular random variable in their linear combinations. So in general, like if you construct a random variable which is a weighted summation of another set of random variables, you want to take the expectation. You can just take the expectation of each individual random variable and do the summation. And the expectation definition can be, I mean, straightforwardly extended to a function random variable. Right? If I want to compute the expectation of g of x, in your integral, you just replace x with g of x. So your homework, there's some problem asking you to calculate like the expectation like e of minus x, right? You really don't need to calculate the density of this. You just shuffle e to the minor x inside the original variable's density. That's it. Right? And also on a discrete case. Oh, all right. Okay, let's stop here today. And next week we're gonna start with some probability distributions, which are very important.
That's-